Yes, hi, Meghna. Hello, Deep Sony. Hello, everybody. Yes. So, guys, am I visible and audible to everyone? And welcome to the JEE Byte session, guys. This is another session where we have, this is Oscillations Part 2. So, in the Oscillations Part 1, what we have done is we have taken some numericals, right? And I have just told you, like, how to figure out the time period and the frequency some system is given to you. So last time, if I just take a brief, just a moment, guys. Yeah, if I just take a brief, like in SHM, in simple harmonic motion, right? So what is happening in that? That acceleration is nothing but proportional to the displacement, right? This is what we have learned last time, right? So whatever the systems is given to you, basically the spring mass, like the spring block system, or maybe the pendulum, or some kind of system is given to you, and you have to just figure out the time period or the frequency. So there are actually two methods. One is you can just figure out the restoring force in it, and you can just directly equate it to minus omega square x, where you can easily calculate the omega, and later on you can just figure out the time period from it. Yes, hi Vismay. Hello everybody who has joined. And second one is the conservation of energy, where you just write the energy of that particular system and you just equate it to the constant. Later on, you just differentiate it and you can figure out the value of omega and all the successive things, right? Time period or the frequency, right? So these are the basic methods. So we are going to take a few numericals on this. Okay, let's just start off, guys. I do have a numerical that was asked in IIT JEE 2009. So here we do have a system where we do have two springs and one rod. Okay. So I'm going to read up this question. A uniform rod of length L, and a mass M is pivoted at the center. At its two ends are attached to the two springs. You can see here the two springs are attached here, right? So the springs have the spring constant as K, right? And the springs are fixed to the rigid supports you can see here in the diagram. And the rod is free to oscillate in the horizontal plane. The rod is gently pushed through the small angle theta. What we have done is we have just twisted that rod to a small angle theta. Suppose this is the rod, and what we are doing is we are just twisting it for a small angle, okay? And what it will do, it will be oscillating like in this way, okay? So we just need to figure out the frequency of the oscillations here. So actually there are two methods. First of all, you can do with the help of the restoring force as well, and one is the energy method. So I generally prefer the energy method, okay, because it's basically, easy to write the energy equation. So any option you can, any method you can opt it, right, and figure out. Okay, so let me just write it here. I do have this spring. Just a moment, guys. Okay, and what is happening here? I do have a spring here. This is the rod, and I do have a spring here. This rod mass is M and the length is L, and their spring constant is K. Suppose I have twisted this rod to a small angle, okay, let it be theta. Or you can just see here that the springs, both these springs are getting stretched by some small amount, that is x. So if you are writing the equation of the energy, if I'm writing the equation of the energy, the total energy here has to be constant, isn't it? I'm just writing it as K. Okay. So what is the total energy? We do have the spring potential energy, as we have two springs. So I'm going to write it up here as 2 into half kx square, right? Plus, as the rod is also moving in this way, so we do have the rotational kinetic energy, that is half I omega square, and that is equals to constant. Right. So what we are going to do is we are going to simplify it. This will become kx square and this will become half. As you can see here, the rod is rotating about the midpoint. So how we are going to write this up? This is m l square upon 12, because this is the moment of inertia of the rod about the axis that is passing through the center, isn't it? So this is omega square is equals to constant. Fine. So now what I'm going to do is I'm going to differentiate it. So differentiate both the sides, okay? With respect to t, so what you are getting, I'm dragging the everything on the next board. So this is kx square d upon dt plus d upon dt of half ml square upon 12 omega square. And if you are doing a constant term derivation, that will give you nothing but the zero. Okay, so this will become 2kx dx upon dt, right? And this will give you ml square upon 24, because everything is constant here. And this will become 2 omega d omega upon dt, right, is equals to 0. So guys, I just wanted to tell you something here. So the spring here is stretched by a small amount x. You can see in the figure here, this is x here, okay, and this is what, l by 2, this distance. So if I am just seeing the triangle o a b, okay, so I'm going to write an equation here. This is, just a moment, this is x, this is l by 2, right? This is the center point of the rod, and this will become, this is x, right? And what is theta? This is theta. So if you're writing sine theta in this triangle, so sine theta will give you x upon l by 2. Or probably if you're calculating x from here, it will give you l by 2 sine theta, or you can write it here as l by 2 theta, because we are just moving it with a small angle, and that is theta, nothing but this theta. Okay, so x is equals to l by 2 upon theta, right? So what I'm going to do is I'm going to put everything, okay, here means in place of the x, I'm going to put in the form of l. So this is l by 2 theta, okay, just a moment, l by 2 theta, and this is v, dx upon dt is nothing but v, and this is ml square upon 24, this is 2 of omega, omega d omega upon dt is nothing but alpha, right? So you know that as this rod is oscillating like in this way, so we can convert v is what, v equals to omega r, right? So you can put it v as omega l by 2, because here it is rotating about the axis that is passing through the center. So I can put it here as 2 k l by 2 theta, and again omega l by 2 plus ml square upon 24 2 omega alpha equals to 0. Let me just put a boundary here. Okay, yes. So here you can see the 2 will get cancelled out, right? And here I'm just solving it, kl square omega theta upon 2, just a moment, kl square omega theta, yes, plus this will become m l square upon, this will become 12 omega alpha equals to 0. So l square and omega are the constant, means they are the common terms, so we can just remove them out, right? And so the remaining terms are k theta upon 2, and here you can see k theta upon 2 and m alpha upon 12, right? Right, just a moment, right? So this is a thing, guys. So I'm going to put alpha here as minus k theta upon 2. This is 12 upon m, right? So this will become 6, and alpha is coming out to be minus k 6k upon m theta. Omega, this one, the alpha is the angular acceleration, and I can just put it as minus omega squared theta, because in the SHM we do have a condition like this. So once you just compare it, you will get it that omega is coming out to be 6k upon m under root, right? Right. So now if you want to calculate the time period, that will become 2 pi under root 2 pi by omega, means m by 6k. Or if you're calculating the frequency, you just need to reciprocate of it. It means 1 upon 2 pi under root 6k upon m. So this is the frequency by which this rod is being oscillating. So let me just see the options here. Yeah, this one, right? So this is the one that we got it, right? So guys, this is how you have to do it. Again, I'm telling you, you have two kind of methods. Either you can go for the energy method, or you can go with the restoring force method. I personally, find this one easy. That's why I always follow this energy method. Okay, so it's up to you. So guys, we do have another question here. Here we do have a mass, and it is attached by two springs that are connected in series. Okay, so yes, what we have to calculate, we have to calculate there is a mass shown in the figure oscillating in simple harmonic motion, and its amplitude is given as a, the amplitude of the point a, we point p. So we need to calculate, once it is being oscillating, we need to calculate what would be the amplitude of this point, what maximum distance it will be away from this, just a moment, from this rigid support. Okay, so you need to calculate that thing. How would you approach this one? How would you approach this question? See, one thing I just wanted to tell you, that in both these springs, once it is oscillating, suppose it is stretched by some amount, right? And they have told us that the amplitude, maximum amplitude, suppose it has reached to the maximum amplitude here, the mass has reached to this point. So you can say here that the total amplitude is nothing, but there is some stretch in this spring x1, and there is some stretch in this spring that would be x2. So I can write it as x1 plus x2, isn't it? I can write that the small, whatever the stretch that is being produced in the one spring, in the first spring, and whatever the stretch that is being produced in the second spring, so that amplitude of that particular system would be nothing but the sum of the individual spring stretch, right? So what I'm going to do is, one more thing just need to tell you guys, these are the forces. Suppose in the spring 1, whatever the force is being developed, you can write it as k1 x1, right? And this, in this spring, the force is being developed as k2 x2, right? Because this is the spring force. This is how we represent the spring force, F equals to kx, isn't it? So you can see here, these are the forces that are internal forces. As this system is not moving, only this particular is moving, right? So these internal forces has to cancel out. So means k1 x1 has to be equals to k2 x2. As these are the internal forces, they must cancel out each other, right? So what I'm going to do is, I am going to produce a relation from x2, and this is the way, right? Fine. So we need to calculate excuse me, we need to calculate how much this point is being away from this rigid, like attachment, right? So what you have to do is you have to just calculate the amplitude of this point P. So what we are going to do is we are going to just calculate the value of x1, right? So A is what? X1 plus x2. A is equals to x1. What is x2? X2 you can write it in the terms of this one. So k1 x1 plus upon k2. So what you are getting is this is k2, just a moment, k2 x1 plus k1, I'm sorry guys, just a moment, k2 x1 plus k1 x1 upon k2, right? So A is equals to k2 x1 plus k1 x1 upon k2, right? Yeah, upon k2. So here you can take out the common x1 from here. So what you are getting, k1 plus k2 upon k2. And from here x1 you can calculate the value of k, value of x, from this equation you can calculate the value of x1, and that is a of k2 upon k1 plus k2. This is the one you will be getting, and this is the amount by which the p point will be stretched. That's what we need to calculate. So this is the option guys, a k2 upon k1 plus k2. So which option should be correct? This one, the D option has to be correct. Okay guys, any doubt as far as these two questions are concerned? They are like, these are the, like, questions they are which are being asked in the JEE from like as far as the last year is concerned. So just have a look guys. Okay, so now I'm taking up one more question here, just a moment. Yeah, so here there is a metal rod, its length is L and the mass is M. I mean, this is a rod here, so its length is, entire length is L, and we do have a disc at the bottom. The rod mass is given as M and length is given as L, and the disc which is attached at the bottom, this is the disc, okay, which is attached at the bottom. It has a mass capital M, and the small mass is represented by the rod. Okay, so R is less than L, they have given us. Okay, so is attached at the center to the free end of the rod. This is the free end of the rod, and it is being attached here. Okay, so consider two ways of the disc attached. We have attached the disc in the two ways. One is the disc is not free to rotate about the center. Okay, so the disc which is being attached, we have just attached that there is no rotation about this, about there is no rotation of the disc about its axis that is being passed through the center. Okay, and the disc is free to rotate about its center. And the second case is one where the disc is being rotated. So there are two cases. In the first one, this entire rod and the disc is totally attached to each other, and there is no movement between these two bodies. Okay, and in the second one, this rod and this disc, so disc can easily rotate at the bottom. You're getting my point? So you have to figure out which option from these four. Okay, this is the rod disc system. So perform SHM, okay, in a vertical plane. So being released from the same displaced position, we have just displaced this from the mean position, and we have just left it. So this is performing SHM. So you just need to figure out which option should be correct one. Okay, so here what you have to do is, what should be your approach? First of all, you know that it is performing SHM. So the first option, if I look into it, so restoring torque in the case A has to be equals to the restoring torque in the case B. Is that, what do you think, whether it's correct or not? So if you just build up an FBD of this particular system, how it would be, this is the mean position. I'm drawing it here, just a moment. Okay, And we do have this one here. Okay, so what we are doing is we have just displaced this particular system, means rod plus the disk, and displaced by some small angle like theta. Okay, so here you can see, as this rod has a small mass m and this disk has a capital mass M, so you can see here the center of mass of the rod is somewhere at the center, right? So here it would be acting like mg, the weight of the rod. And here you can see the weight of the disk is acting in this position, means vertically, that would be capital Mg. So if you see what would be the restoring force is nothing, you can just resolve these one here. This is theta. This would become mg, capital Mg sine theta. And here also, if you resolve these two, so it will become small mg sine theta. So a small mg sine theta and the capital Mg sine theta will be responsible to produce the torque, isn't it? Right? So if I'm writing the torque equation, right, or you can say the restoring torque is nothing but here you can see that mg sine theta, right, this is the force into L, right, plus for this one this is also providing the torque, that is mg sine theta, right, into L upon 2, right? So this is the restoring force. And if we talk about the second system as well, so again the same thing is being happened, because as far as the disk rotation is concerned, there won't be any effect on the restoring torque. So we can say here, in the case of the restoring torque in the first case A and the restoring torque in the second case B, they are nothing but equal. Okay, so the first option we can easily say that they are, this is absolutely correct. The restoring torque in the case 1 and the restoring torque in the case B are same. But this question is not like completed yet. So this is like, you can say here, you can see here which of the following statements is or are true. So this may be one or more than option correct. Okay, more than one option correct. So restoring torque, this is already we have neglected, right? Because restoring torques are equal, so no need of this inequality signs. What about the angular frequency, guys? Angular frequency for the case A is greater than the angular frequency for the case B, or angular frequency for the case A is lesser than the angular frequency for the case B. So which one should be correct? As far as angular frequency is concerned, we can just take it up in this way. If we talk about the energy, so if we talk about the energy, how would we proceed? See, once, just a moment, guys. Once we are taking this one, okay, I do have the system like in this way. Okay, so here if I'm taking up, you can see here both the system are raised up to a same height. So I can say here the potential energy is developed in the case A has to be equals to the potential energy is being developed in the case of the B. So once you just leaving them, so what is happening, they will be acquiring some kinetic energy, isn't it? So for the case A, the kinetic energy I'm writing, so what would be the kinetic energy? Because it is having only the translational motion, because there is nothing rotation, right? Because the disk is not free to rotate in this. So what I can write it here, half m plus small m, and I'm writing at the velocity of the center of mass of this particular system is Vc in the case of A square. This is the kinetic energy in the case of A, isn't it? What about the kinetic energy in the case of B? That would be half m plus a small m Vc B square, but there is one more kinetic energy, that is nothing but half I omega square, because it is rotating around the axis that is being passed through the center, right? So we do have the kinetic energy this much. Okay, as you can see here, both the potential energies are getting converted into kinetic energy, so their kinetic energies has to be equal. So here what we can do, that Ke in the case of A has to be equals to Ke in the case of the B, right? So what we are seeing here, as these two energies are equal, you can see here, and you can see here that this B term is more than this term. So you can see here that V of CB has to be less than VC of A, isn't it? Because if you're making them these two equations equal, so the velocity in the case of this means the linear velocity in the case of B has to be less than the linear velocity of A, right? Right, guys? If you are comparing it with in the case of this one, omega r, V is nothing but the omega r, right? So you can see here that the omega of B has to be less than of omega of A. So the angular velocity in the case of the B is less than as compared to the angular velocity of case A. So here you can see that the angular velocity, sorry, we are right, the angular frequency means the omega, nothing but the angular frequency, right? So the angular frequency in the case A, you can see here, is more than the angular frequency for the case B. Okay, so this option is correct. Fine, guys. Anything else? Any doubt you want to like discuss here? Yes. So guys, that's all from my side as far as today's session is concerned, this YouTube session is concerned. Okay, you can check out these links as well. And the second thing, guys, one more thing, one more notification, we are going to launch the all India test series for JEE as well as NEET aspirants. Okay, so you can check it out, and it is going to start from the 6th of November. Okay, so these are the important notifications, right? So we do have 8-part test and the 15 full test here. Okay, and for more information you can check it on the website. Okay, thank you so much, guys, for attending the session. I'm going to wind up the session now. Thank you so much. Bye bye, take care.